Hello everyone, we've got our chapter 15 video today, which is on random variables. So the learning goals for chapter 15, of course we want to define what a random variable is, but then we want to be able to calculate probabilities of random variables using a calculator. And we also want to use the addition rule for expected values and variances of random variables to calculate population means and standard deviations. That's a lot of words, but you're going to see here in a moment, it's really not too complicated. So to start off, let's think about what a random variable is. If you guys remember up to this point, we've asked, for example, what is the probability of being male if we pick someone at random? Or what's the probability that they play a certain sport? Well, a random variable, instead of writing out all this lengthy word stuff in our probability notation, it is just a shorthand way to represent a quantitative variable. So if we want to know what's the probability that we have two siblings, okay? Well, the random variable would be the number of siblings that we have, but instead of saying number of siblings is equal to 2, we just denote it with a shorthand like a variable x, for example, a capital letter X. And that can denote what our random variable is equal to. And then for our variable, we have different values that that variable can take on. So you can have 0 siblings, you could have 1, you could have 2, you could have 3, maybe we go up to 5 or 6, okay? So random variable really is just a shorthand notation of something that we've seen before. We have our variable name, which is denoted with a capital letter, and then the lowercase letter are the values that that variable can take on. When it comes to random variables, we have two primary kinds. The first one is a discrete random variable, and this is where within a range of values, we have a countable number of possible outcomes that variable can take on. So for example, number of children, that is going to be an integer value. It is 0, 1, 2, 3. So if our range of values is between 0 and 5, there are numbers within that range that our variable cannot take on. For example, you can't have 4.5 siblings. So because there is some number in our range of values that our variable can't take on, that is why it is considered discrete. Same thing with shoe size. If we have a range in the classroom of size 5 shoe all the way up to size 14 maybe, there are sizes or numbers within that range that the variable cannot take on. There is no size 13.763 for a shoe, so that would be discrete as well. Continuous, on the other hand, this is where there are an infinite number of possibilities that a variable can take on. So temperature, for example, if our low temperature for the day is 20 degrees and our high temperature is 40 degrees, well, we know at every point within, or at some point throughout the day, we hit every single value within 20 to 40 degrees. There's no number within that range that our variable cannot be equal to. And same thing with like a distance traveled to work, that can be any value between 0 and however many miles. So discrete, that's where we have a countable number of outcomes that our variable can take on. Continuous, that's where you have an infinite number of possibilities. Once we've defined what our random variable is, then we can come up with what's called a probability model for that random variable. A probability model includes two different things, and I'll show you an example here in a moment. The first thing it has to have is all the possible values that your variable can take on. So if we're talking about number of siblings, maybe we go 0, 1, 2, 3, 4, 5, 6, okay? Then with each of those values, we also have to have the corresponding probability that each value occurs. So what's the probability of having 0 siblings, or 1, or 2, or 3? So if you have both of those components, that's what we call a probability model. Another example for more of a continuous variable would be the weights of adult Siberian Huskies. So obviously that's going to be a continuous variable. A husky could be any weight within 20 to 110 pounds. So how this is going to be different is that instead of stating exactly what values our variable can take on, we might provide a range, maybe 20 to 30 pounds, then 30 to 40 pounds, 40 to 50, and so on, and then have those corresponding probabilities. Typically, what we're going to be interested in when it comes to a random variable is what can we expect that variable to be equal to, okay? So if our random variable is the number of siblings that you have, we might want to know if we pick someone at random, how many siblings can we expect for them to have? Or if we're talking about shoe size, we might want to know if we pick anyone at random, what shoe size can we expect them to have, okay? So up to this point, if we think back to the normal curve, we have the mean in the middle of that normal curve. That is what we could consider our expected value in a normal model. What we're going to say now, instead of that mu or that mean symbol, we are going to now have a new notation called E of x, or the expected value of x. Now, this looks like a slightly complicated formula, but really it's not too bad. You see we have the sum symbol, meaning we're going to be adding, and then we have x times the probability of x, okay? In other words, we are going to take every possible value for our random variable, multiply it by its corresponding probability, and then add that to all the other possible outcomes and their probabilities. So let me show you an example of this. I think you'll do just fine once you do see an example. So let's say that our situation is here we've got a probability model for the number of robocalls that you're going to receive in a week, okay? So we see that our possible outcomes are 0, 1, 2, or 3. And then we have the corresponding probabilities of each of those outcomes. So the probability of having 0 calls is 0.1, having 1 call is 0.3, and so on. So this is exactly what a probability model is. We have all possible values of our variable, 0, 1, 2, or 3, and then we have the corresponding probability of each of those events happening, okay? So to find out or answer the question, how many calls can you expect to get each week, this is where the expected value comes in. So we're going to take each of these individual number of calls possible, multiply them by their corresponding probability, and then add it to the other ones. So let me flip over to this next slide and I'll show you how it's done. So you can see my work here. I'm going to take 0 repair calls, multiply that by 0.1, the corresponding probability. To that, I'm going to add 1 times 0.3, which is the next column in our probability model. I'll add that to 2 times 0.4 and add that to 3 times 0.2. So this is exactly what it means to find the expected value. And when you sum all of these together, these 4 different probabilities and their outcomes, we get 1.7. So that means based off of our probability model, we would expect to have 1.7 calls per week. Okay, so we've talked about center, or that expected value. Now let's talk about how spread out our distribution is. So if you guys remember, we talked about standard deviation. That basically is a way to quantify how spread out our data is. And we talked briefly about something called variance. Variance is just the standard deviation squared, okay? So when it comes to the variance, we first need to find that before we find standard deviation, because we're going to find that variance, take the square root of it, and then that is our standard deviation, okay? So if you even remember slightly about what variance is or standard deviation is, it's from before, it's very similar to that. We're going to take each individual value, so in this formula, that is x, minus mu, which is our mean or expected value, square it, and then the new part is we're going to multiply it by the corresponding probability of that x value, okay? Then we're going to do that for all the other possible values, add them up, take the square root, that's our standard deviation. And I should tell you, I should have prefaced with this, we're going to learn how to do all of this on the calculator, so don't feel like you need to memorize how to do this by hand. So going back to our first example about the number of calls that we get, we already found that that expected value is 1.7, so our mean or expected number of calls is 1.7. To find our standard deviation, let's first find our variance, and then we can just take the square root of that. So like I said, we're going to take each possible value, so 0, 1, 2, 3, and subtract the expected value from that. So 0 minus 1.7, 1 minus 1.7, 2 minus 1.7, and so on. We're going to square that number and then multiply it by its corresponding probability. We'll do that for each of these 4 possible values. We'll add them up, and that will be our variance. So let me show you that on our next screen. Okay, as you can see here, the numbers, the 1.7 stays the same because in our formula, we're taking minus our expected value, which is 1.7. So that's going to stay the same all throughout. But on our first one, we're taking 0, our first possible value, 0 minus 1.7, squaring it, and multiplying it times the probability of 0, so 0.1. To that, we're going to add 1 minus 1.7, that's our next possible value, square it, and then take it times that corresponding probability of 0.3, and then continue this for 2 and for 3. If I simplify a little bit, that's what my next line is. I've got negative 1.7, negative 0.7, 0.3, 1.3, and so on. So if I put all of that together, I get 0.81, and that is my variance. So again, to find standard deviation, I just take the square root of that. Like I said, you do not need to know how to do this by hand. I just want to show you how this whole thing works, but in class, I will show you how to do this on your calculator. I know I just said I'll show you how to do this on your calculator, but I wanted to show you this cute baby in a TI-83 costume. The last concept of random variables is the idea of combining data together. So going back to what we've talked about in the past, if you remember, if we had a set of data and we added a constant amount to all of our data, I want you to think about how did that affect the mean of our distribution? And how did it affect the standard deviation of our distribution, okay? So if we have a set of data, we added the same amount to each piece of data, how did that affect the mean? How did that affect the standard deviation? Well, if you remember, measures of center were affected because if our mean score was 50, we add 20% to everyone, that shifts it up by 20, so our mean becomes 70. But standard deviation and other measures of spread were not affected. So that's actually going to be the same case when it comes to random variables. So as you can see here, if we add a constant, let's say C, just some constant number, or we subtract it from our set of data, then the expected value or the mean changes by that exact amount. So if we add C, we just add C to that expected value. If we subtract C from all of our data, we subtract that C from our expected value as well. On the other hand, variance and standard deviation, those are not affected. So if we add or subtract a constant to our set of data, that is not going to affect our measure of spread at all. So I think one of the more common examples we saw in the past is if we gave everyone a $5,000 raise at a business. Well, that's going to shift up the mean salary by 5,000, but that's not going to affect how spread out our data is. Now, on the other hand, we had the idea of scaling our data. So if we multiplied all of our data by a constant, that had a more significant impact on both the mean or the center and our spread of our data. So when you multiply all of your data values by a same constant value, that's going to affect both the mean and the standard deviation. For random variables, it is slightly different how that's affected. So let's take a look at that. In the case where we multiply all of our data by a same constant value, you can see that the expected value, all we have to do is multiply it by that same amount. So if we multiply everything by a constant A, in the expected value, we just take that times A as well. Variance, on the other hand, because variance is standard deviation squared, we can't just multiply it by A. Our variance, we have to multiply by A squared. Okay, and that way when we take the square root of it, we actually just multiply standard deviation by A. So both expected value and standard deviation, we're going to multiply by A. Variance, we have to multiply by A squared because that is the square of standard deviation. Okay, so a situation like this might be if everyone at a company gets a 10% raise, we're going to multiply everyone's salary by 1.10. And our last thing here, oftentimes when it comes to distributions, we actually want to combine distributions. So if you're familiar with anything in marketing where you're talking about profit, profit is equal to your revenue minus your expenses. So if we have a distribution for revenue, we have a distribution for expenses, then we could subtract those two together or from one another, and then that would give us our profit distribution, which might be really useful. Okay, so if it's the case that we are adding or subtracting two distributions together, or combining them in some way, adding or subtracting, then the expected value is exactly either the sum or the difference of the two individual expected values. So if we wanted to take our revenue minus our expenses, then the expected value for profit would be the expected value of revenue minus the expected value of our costs. Okay, so it works just like you think it should. If you add them together, you add the two expected values. If you subtract them, you subtract the two expected values. Okay. On the other hand, when it comes to how spread out our data is, first thing, we cannot just add or subtract standard deviations. We actually have to convert to variance first, then combine them, then take the square root, okay? And the key thing when it comes to the spread of our combined distributions is that if you combine two distributions in any way, it's always going to become more spread out than the two individual distributions on their own, okay? So whether you are adding or subtracting two variables together, to find the new variance, you are always going to add the two corresponding variances together, okay? So for our profit example that I just talked about, we're going to take revenue minus our expenses. So for our expected value, we would just take revenue expected value minus our expenses expected value. But for variance, even though we're subtracting the two distributions, we actually want to add the two variances together. And then once we do that, we can take the square root of it. That would be our new standard deviation. So whether you're adding or subtracting two distributions together, you always add your variances together. Expected value, if you subtract them. If you add them together. And this idea of having to square, then add, then take the square root, that's what we refer to as the Pythagorean theorem of statistics. So if you are combining two variables together, you have to first square the standard deviations separately, add them together, then take the square root. So you can kind of visualize it as a right triangle using that Pythagorean theorem. So where are we going with this? This is our last slide on this video. If you remember way back, it was Unit 1, we talked about the normal curve. We saw that there's some really useful properties when it comes to the normal curve. In fact, if we can use the normal curve, we want to, because then we have normal CDF, we have normal PDF, we have inverse norm, all those really handy calculator functions. So because random variables have an expected value or a mean, and we have a standard deviation, and if we are told that they are approximately normal distributions, then we are able to use those helpful properties of the normal curve. So that's where we're going to be heading moving forward, not so much this unit, but in units in the future. Just know that random variables are closely related to our probability for the normal curve.